Okay, Assalamu alaikum. Good morning, everybody. Today we will continue our class. Last time we stopped at proposition 1 for Euclid, that for any segment AB, we can draw an equilateral triangle. We can draw an equilateral triangle that all the sides are equal to AB. All the sides are equal to AB. Just we will use the ruler and compass. First, we have the line segment AB. Then from B, we will draw a circle with radius AB and center B. This one. We will draw a circle with radius AB and center B. Draw another circle. We will center at A. Then we will draw a circle with radius AB. Then we can, for the point of intersection between the two circles, we can draw the two segments. If you call it C, for example, then AC is equal to CB is equal to AB. We claim this is an equilateral triangle. To prove this an equilateral triangle, we have for the first circle, we have that CB is equal to AB because both are radius. For the second circle, we have that AC equal to AB. AC is equal because both are radius for the second circle. So now I have CB is equal to AB, CA also equal to AB. So this means that CB equal to AB equal to AC. So this is the equilateral triangle. So starting from any segment, you can draw an equilateral triangle. And this is the proof. You have to know the step of how to draw and how to prove. So given a segment AB, this is the given information. You can draw a circle with center A and radius AB using the axiom 3 for Euclid. You can draw another circle, but this time the center is B, the same radius, BA, also by using axiom 3. Then C is the point of intersection. Now you can construct between A and C a segment and C and B a segment using the axiom 1 of Euclid, that between 2 points you have a segment that connects these 2 points. Now, since AB and AC radius of circle 1, CB and AB are radius of circle 2, then AC and CB and AB are all equal. Then you have ABC is equilateral triangle. So this is the proof. Today I need to go for the second proposition. For second proposition, this one we will use the straight line. We can place or we can draw a straight line equal to a given straight line with one end at the given point, which means that if I have a point A, for example, and I have a segment CB, this is the given information that you have a segment CB and a point A. So this proposition states that you can draw another segment AE. This segment is equal in length equal to CB. AE, or this one, that is the blue one, equal to CB, which means that from any point, I can draw a segment equal to a given segment. If I have a given segment, CB, I have a point, I can, by using also compass and ruler, I can draw a segment, another segment equal to CB, Okay. So now we need to go to see how we can do that and how to prove. So I will go here. Hopefully you can see my screen. So the given information is that I have a point A and I have another segment. I don't know its length. I don't know the length of CB. I just have a point and I have a segment BC. What we need to plot now or to draw now, I need to draw from A another segment equal to BC. Even I don't know how is the length of BC, but I need to draw a segment from A equal in length to BC. Hopefully you have your compass and ruler and paper and start to draw with me. So this is the point A. This is the point AC. The first step I will do that I will plot from A to C another segment here. This can be done from axiom 1. Axiom 1 for Euclid stated that if you have 2 points, you can draw a segment between them. If you have 2 points, you can draw a segment between them. So I will draw a segment AC. The second step, I will draw, since AC is a segment, then I can draw an equilateral triangle. I can draw an equilateral triangle. Okay, so if I draw an equilateral triangle here, this is by using proposition 1. This is by using proposition 1. Proposition 1 states that if you have a segment, you can draw an equilateral triangle. So I will draw an equilateral triangle using a proposition 1. So here, this is an equilateral triangle. So the first step, I connect A and C by a segment. The second step, I draw an equilateral triangle. This is by using proposition 1. For any segment, you can draw an equilateral triangle. Now, for the second axiom of Euclid, that any segment can be extended to infinity. Any segment can be extended to infinity. So I will extend DC, this one, and also DA. I will extend these two circles. How can I do this? Because second axiom of Euclid states that if you have a line segment, you can extend it infinitely from both sides. So I will extend DC, and also I will extend DA. I will extend DA. Now what I will do is I will draw a circle, because the third axiom of Euclid states that if you have a circle and you have a center for this circle, then you can draw, if you have a point and you have a line segment, you can draw a circle. The center is this point and the radius is this segment. So I will draw from C here, I will draw a circle with radius CB, this one. So here, okay, like this. So I will start from point C. I will draw a circle with radius CB. Now I will let this point of intersection. This is my point of intersection here, E. Now I will draw another circle. I will draw another circle. But this time my center will be D, not C. The point D, the radius will be DE, this one. Like this. So here you have another point of intersection. Make it equal to F or any point. So now if you look for AF, this one, this is a line segment from A and equal in length to CB. This is a line segment from A and equal to CB. How it is equal? We need to prove this one. So if you look for this circle, this one that's center B, CE is equal to CB, right? CE is equal to CB. Do you know why? Why CE is equal to CB? Why CE is equal to CB? Yes, both are radius for the same circle. So CE is equal to CB. Okay. And also I have look for DE. Okay, and this one. Look for DE and DF. DE or DF. Both are equal, right? DE and DF. Are they equal or not? DF, this line, and DE. Yes, because are both still the radius of the same circle, the bigger one, the bigger circle. Okay, what about DC and DA? DC, DA, are they equal? DC and DA, these two lines. Are these two lines are equal or not? Yes, because this is an equilateral triangle, this one. So DC is equal to DA. Now, if I look here, I have that DE is equal to DF. DC is equal to DA. This means what? What you can conclude from that? What you can conclude from that? DE, again, equal to DF, DC equal to DA. What you can conclude? AF equal to CE. Yes, correct. EAF is equal to CE. Because I have that DE, this one, equal to DF. This is our two radius of the circle. And this is the small part is equal to the small part here. So for sure, the rest will be equal to the rest from using the notations of Euclid. AF will be equal to CE, will be equal to CE. And CE is equal to CB. CE is equal to CB. So this means that CE is equal to CB and CE also equal to AF. So we can conclude that CB and AF should have the same length. CB and AF should have the same length. So from the same point, you can draw a line equal in length to CB. Equal in length to CB. So again, what you did, first of all, I have a point A and line segment CB. So the first step, I draw the line AC using axiom 1. Then I draw using proposition 1, I draw an equilateral triangle, ADC. Then using axiom 2, I extend these two lines, DC and DA. Now from point C, we can draw a circle equal to, the radius is equal to CB. So this is the first circle. And the intersection point here will be E. Now, from D, I need to draw another circle with radius DE, with radius DE. So this is the second circle, and this is the second intersection point, F. So now I have AF. I claim that AF is equal to CB in length. To prove that, you have that CB is equal to CE radius of the small circle, and DE is equal to DF, the radius of the bigger circle, and DC is equal to DA because this is an equilateral triangle. Now, since DE is equal to DF, DC is equal to DA here, you can subtract these two equal parts, so the rest is equal to the rest. CE is equal to AF. So you have AF equal to CE equal to CB equal to CB. So the three are equals. So AF for sure should be equal to CB. So from any point and any line segment, you still can draw a line equal in length to CB, equal in length to CB. And this is the proof here. This is the proof here. A is a given point, PC straight. Then you need to draw a circle with center B and radius BC. With center B and radius BC. Here the intersections points are G and L. Now G is the intersection point with the circle with ray BF. So we can construct another circle, GKL, with center D and radius DG. So I will construct another circle with center D and radius DG here. Then we claim that this line is equal to this line is equal to this line. So we will assume that the point of intersection is L. And since D is the center, then DL equal to DG. If you subtract the equilateral parts, sides of the equilateral triangle, you will have that AL equal to BG. And also we have BG is equal to BC, so all are equal. So all are equal. So please, you have to know how to draw and how to prove. The fourth proposition, proposition 4. Okay, this is proposition 4 about congruent triangle. If you have two triangles, A, B, and C, P, Q, and R, and you have QR is equal to BC, this is the first side. QP is equal to BA, this is the second side. So the first side is equal to the first side. The second side is equal to the second side. And the angle is in between is equal. The angle Q here is equal to the angle B. The angle Q is equal to the angle B. So we claim that both triangles are congruent. Both triangles are congruent. If two triangles have two equal pairs of sides, and the two angles between these sides are equal, then the triangles are equivalent or congruent. The triangles are equivalent or congruent. This theorem, we call it SAS, side angle side. Side angle side. Okay, how we can prove this? Actually, Euclides, he don't have a definitions for congruent triangle. So what he do, usually Greek people, what they do to prove the congruent, they just draw the two triangles with these conditions, BC equal to QR, QP is equal to BA, and the angle is equal to the angle. And then they try to move. They cut one triangle and put it on the second triangle. If they are exactly same, identical, we can say that they are congruent triangle. They based on this kind of transformation to show the congruent between two triangles. So what they did actually, they go for, here, delete this one. I will draw two triangles with the same condition. The side equal to the side, angle equal to the angle, the secant side equal to the secant side. So I have these points. Okay, now from each point I will draw, for example, the length is 4. Okay, here all the same length. So now I have two equal sides. I have two equal sides. This one, make it red, is equal to this one. Now I will draw the same triangle, the same angle. I will draw the same angle. For example, 60 degrees. Sorry. 60 degree. Here also same 60 degree. And I will draw AC and AD. They will be also in the same length. AC equal in length to BD. We can make it this one in green to know that they are equal. Now I will complete the triangle. This one and this one. So now I have this one, BD is equal to AC. BD is equal to AC. The angle here is equal to the angle here. So I claim, or Euclid claim, that this triangle will be exactly same with the second triangle. How he can do that? He just take this one and try to move and put it on the other one. So they both are congruent or same, exactly same, exactly same. So he just cut the first one, move it on the second triangle to show that both are exactly equal. This is the way of proof that the both triangle are same. Just cut the first one, take it, and put it on the second one. So they should both are equal. Both are. Should are equal. That both are. Both triangle are exactly same. So this is the way how Euclid's prove the second proposition of congruent triangle. This is actually proposition 4. We didn't prove proposition 3. So how to prove proposition 4? Let the two triangles, this is the given AC, CD, DF also equal. The angles are equal. We have BC equal to QR, BE equal to QP. The two angles here are equal. The two angles here are equal. Now, if the triangle ABC is applied, which means translated to lie on the top of the another triangle, we will cut it and put it, place it, position it on the top of the second triangle. We will see that both triangle will be exactly same. So when I take it and put it on the second triangle, I will make it I will put the line QR over the line BC. I will put the line QR over the line BC. Since I have the same triangle, for sure BA will be over QB. Will be over QB. So all triangle will be coincide. All the triangle, the straight line AC will coincide with the line DF. Point C will coincide with point F. Base BC coincide with the base EF. Thus, triangle ABC will be the same or equivalent to the triangle DEF. Why? Because both are exactly, all the parts are exactly lines on each other. So this is the way how we prove. There is no steps, mathematical steps. We just cut the first triangle, put it on the second triangle. We just move. Now for the next proposition. Proposition 9. Now we prove proposition 1, 2, proposition 4, now proposition 9. Proposition 9 states that we can bisect any angle. You can bisect any angle. Bisect means that you can divide the angle into two equal parts. You can divide the angle into two equal parts. If you have the angle BAC, then you can divide the angle into two equal parts exactly. How can we do that? Okay, we go here again. Just delete this one. Okay. Now I have an angle. The angle AP. We need to draw an angle. Sorry, angle with different sides. And make it, for example, 80 degree. Okay, so we have this angle is around 80 degree. This is the line segment here. This is the second line segment. Now this is the angle 80 degree. I will bisect this angle into two angles. Each one is 40 degree. Each one is 40 degree. So the first step that I will do is I will take any point on AB. I will take any point on AB. On AB. So I will take any point. Let's follow the same. We call it D. We call it D. For example, we can take it so we will take any point C. Okay, AC here we have, and AC have length 3. So you can take any point with, okay. Here I just make it 3 centimeter, but you can take any point, 2, 3, 4, not necessary. Any point is okay. Now AC is a segment, so from A I can draw, based on proposition 2, I can draw another segment equal in length to AC. Equal in length to AC. So I will draw another one equal in length. Equal in length, this one. So now AC is equal to AD. AD is equal in length to AC. So just take any point on AB. Now draw a line equal in length to AC here on the second AD. So AC is equal to AD. Now you need to connect, because 2 points, you can draw a line between them. And we can draw, because we have now a segment DC, so you can draw an equilateral triangle based on proposition 1. You can draw an equilateral triangle. So I will draw an equilateral triangle. So here I draw an equilateral triangle based on the line CE. Then between A and point E, I can draw based on proposition 1 again, axiom 1, sorry, we can draw a line. We can draw a line, AE, this one. So we claim that this line will bisect the angle. This line that I draw will bisect the angle. Why? Because if you look here, now I have this line. This line is, if you look for the triangle ADE and ACE, these two triangles. Now you have AE is the same or common side between both. Okay, this side is common side with the triangle ADE and ACE, this triangle. So this is a common side. Okay, you have this one, AD is equal in length to AC. AD is equal in length to AC because we draw AD equal to AC. And we have that this one, DE, is equal to EC from the equilateral triangle. So UDE is equal to EC from equilateral triangle. AD is equal to AC because we draw AD equal to AC. We have this one is a common side between the both triangles. So these two triangles are congruent by using SSS, side, three sides. So since both triangles are equal or congruent, sorry, then the two angles here should be equal in measure. Should be both for 40 degrees. And this is the step here. We have the triangle CAB. We draw AD. We take any point on AB. Let's say D. Then by using proposition 3 that you can construct a point E on a segment AC by making the segment AE equal to the line AD. That's the one that we prove. If you have a point, and you have a line segment DA, if you have a point A and have a line segment AD, from the point A you can draw a segment equal in length to AD, So we can do that. AE is equal to AD using proposition 3. Then you can construct line segment DE. You can construct this segment because between any 2 points you can construct a line. This is axiom 1. Now on DE, construct equilateral triangle. This is proposition 1. For any segment, you can draw an equilateral triangle using proposition 1. Then construct the ray AF. Between 2 points, you can construct a line or a ray AF. Now these 2 triangles should be congruent triangle. Consider the triangles ADF and AEF. We have AD equal to AE by construction. We draw this one, AE equal to AD. And we have DF equal to EF also by construction because we draw this equilateral triangle. And we have AF common to both triangles. So the triangles are congruent and the 2 angles are equal. These 2 angles will be equal. CAF, PAF will be both are equal angles. So this means that the ray AF bisect the angle BAC. This means that AF bisect the angle CAB. This one. The ray AF bisect the angle CAB. So this is how we bisect the angle. if you have a triangle A, B, and C, if one of the sides be produced, the exterior angle is greater than either of the interior and opposite angle. Which means if you have a triangle ABC, and I extend one of the ray here, so you will have exterior angle. You will have exterior angle. We claimed that this exterior angle will be greater than both inside angles, will be greater than this one, the interior and the opposite. The interior and the will be greater than both. Greater than both. How we can prove this one? How we can prove this one? So first, you have the triangle ABC. This is the given information. You have a triangle ABC, and the side BC can be extended to the point D. Can be extended to the point D. We have the triangle ABC, and I extend BC to the point D. Now, let the point E bisect the line segment AC. Now, I have AC. I will take E exactly the midpoint. Exactly the midpoint, which means that AE will be equal to this one in length, will be equal to this one. AE is equal to EC, bisect. Can we do that? Actually, we can do that using proposition 10, but we didn't prove proposition 10 for you, but this is a proposition 10 that you can, any line segment can be bisected, can be bisected. Now we need to construct the segment BC, extended it to point F. Now here, go ahead, BE, this is, now I have a point E and a point B. We can draw a line segment BE using axiom 1. And we can extend it using axiom 2 until the point F, until the point F. So, and then draw the line from F to C, because two different points can have a line segment between them. So you can draw FC. Now we will have two triangles, EFC, this one, and AEB, this one. These two triangles, we claim they are congruent triangle. They are congruent triangle, ABE and CFE. ABE and CFE, these two triangles, this one and this one. Okay, why they are congruent? We have AE equal to EC, and we have this angle equal to this angle by vertical angles. And we extend E until we have EF equal to BE. Sorry. When we extend such that BE equal to EF. This is by construction. We extend this one equal to this one. We extend until point F such that EF equal to BE. So now these two triangles are congruent because EF equal to BE, AE equal to EC, two opposite vertical angle. So we both are congruent triangle. Now from congruent triangle, you have that angle 1 will be equal to angle 2. And angle 3 here will be equal to angle 4 from the congruent. Angle 3 will be equal to the angle 4. And we have, if you look for this angle, you call it angle 5. Angle 5 for sure greater than angle 4. This is a notation or axiom, notation for one of Euclid, that the whole is greater than the parts. The whole is greater than the part, notation 5. So 5 is greater than 4, and 4 equal to 3, which means that 5 equal to 3, or greater than 3. 5 greater than 4, 4 equal to 3, then 5 should be greater than 3. Greater than 3. So which means that this is 5 is our exterior angle. Angle 5 is our exterior angle. Is our exterior angle, and sorry. And this is the angle that we need to prove that it is greater than it. So 5 is greater than 3. 5 is greater than 3. By the same way exactly, you can prove that your angle, this one, ACD, is greater than ABC. We can prove this one is greater than ABC by using the same approach. By using the same approach, we need to bisect the line BC. You need to bisect this line by a point and do the same step again to prove that 5 is greater than this one, this angle. So again, what we have ABC is a triangle. We extend the ray BC until the point D. And we need to prove that angle 5 here is greater than angle 3 and this angle. To prove this one, I will first, AC will be bisected by the point E, which means that AE equal to AC. Then draw the line ligament PE and extend it until point F, such that EF equal to EB. EF equal to AB. Then draw the triangle or the line segment FC. Now the two triangle ECF and AEB are congruent triangle. We have two vertical opposite angle. Two sides are equals. Then the two triangles are congruent triangles. Now from the congruent we have 3 is equal to 4. This one, angle 3 is equal to angle 4. And from notation 5 for Euclid, angle 5 for sure greater than angle 4. So angle 5 for sure greater than angle 3. By the same way, you can prove that angle 5 is greater than angle ABC by bisect the BC. Same way, you take a point, bisect the point here, then extend the line and follow the same steps. Follow exactly the same steps.